Hello. So this part is in continuation to the previous part. So I was discussing about the M value. So basically, M can be calculated by using FB into Z. So I have just told you that this, this formula is derived from the bending equation. So in this, this is bending stress and Z is the section modulus. So section modulus is very important. So if we want to have maximum moment of resistance, maximum strength of our beam, in that case, Z should be higher. And Z is dependent on the dimensions of the beam. So which means if the dimensions of the beam is on the higher side, then Z will be on the higher side. So now FB, this is basically the stress. So now here we are calling stress corresponding to this graph, which is the idealized graph. So now in the second point, if we take the second point, so at this point you can see the stress is corresponding to the yield stress. So at that time we will say that the load that we have increased, this P load is further increased, and after increasing that, the stress which is generated will be equivalent to the Fy at point 2. So at this position, we can say that the maximum stress in the beam will be F2, which will be equivalent to the Fy value, while at the neutral axis, the stress is 0, and the variation of this stress across the depth will be linear, which means at the topmost point and on the lowermost point, the stress is higher, and as we go towards the neutral axis, at that point the stress is 0. So the stress on the upper part of the neutral axis will be in the compression, and stress on the lower part will be in the tension. So at this stress value, the moment of resistance or the strength of beam will be equivalent to the strength of beam at yield strength. So in that case, my will be equals to Fy into Z. So you can see here, now this becomes the Fy value for the second case. Similarly, now if we try to find out, uh, I mean, at this point, the uppermost fiber is yielding, while the fiber between the neutral axis and the uppermost fiber, they are still in the stress within them will be still less than the Fy value. Now, on further increment of the stress, if we further increase the load, what will happen? Now, the stress in the beam will not increase more than Fy value, but what will happen? The stress will be redistributed, and now the lower part of the beam, the increment of the stress will be inwardly, which means in the second part, the yield strength was up to this line. Now, when we further increase the load, in that case, now the yield strength, say we can say that this I section is yielded up to this point. So you can see here, corresponding to this, we can say that this much part of the beam is yielded, while this part is still in the elastic region, which means this part is yielded, which means it has reached in the plastic zone, or plastification is happening in the upper part, which I have just hedged. Similarly, the same thing is happening on the lower region also, like up to this part. You can see here, corresponding to this. So this part is also plastifying. So this part is plastified, while this part is still in the elastic region. So the moment of resistance at this stage, which is 0.3, at this stage will be the sum of moment of the moment of resistance in this region. We can say that it is because of the plastification, and moment of resistance because in this region and in this region will be because the material is still in the elastic region. So basically the value of M will be M1 plus M2. Now this M1 is because of the plastification, this part and this part, and M2 is because some part is still elastic. So this M2 will be due to this part, and corresponding to this part and this part. So this M value this time will be uh, between My and Mz. Sorry, MP. Now MP is called plastic moment. Now plastic moment is the condition when the whole material of the section is yielded. So basically you can see here, uh, in this case what is happening actually is in this it is in the elastic range. Now in this it becomes plastic as well as elastic. So this part up to this part it is elastic, and this part becomes plastic. Now when we further increase the load, then what will happen? The stress will again increase inwardly. I mean, stress will not increase, but the same stress will reach to the zone where the material is still elastic. So this increment of the stress will be like inwardly, and similarly like in this direction. So you can see the next diagram. In this we can say that the whole material of the beam is yielded. Similarly here also whole material of the beam is yielded, and at this stage the moment of resistance or the strength of beam, I mean if such condition occur in the I section, in that case the strength of beam will be equivalent to the MP value. Now MP is plastic moment, and at this stage the hinge in the I section will develop. That I will show you using the diagram. Now the same diagram, now we will follow the same diagram in this case. Now consider this is the beam on which we are actually applying the load, which is say W. Okay, and this beam is actually I section. So when we were at this position, in that case this second diagram, this is actually the bending moment diagram. So because of the central point load, bending moment diagram is something like this. So this one diagram is corresponding to this point when the stress in the beam is lower than the yield strength or yield stress Fy value. Similarly on further increment, this one you can see here, this one on further increment you can see the diagram is increasing, which means the moment I mean area of bending moment is increasing, which means the M value is equivalent to the My. Similarly on further increment, M value is between My and MP. And on final, I mean when the whole section becomes plastic, in that case the moment of resistance becomes equivalent to the MP. And at this stage you can see, at third point you can see some part is plastic and some part is elastic. Now the part which is plastic, it is being shown here. So this part is plastic, and this is actually forming the hinge. Now when the complete part is plastic, you can see here, so this whole part, the shaded part becomes plastic, which means it can rotate now freely. It can rotate. So this condition, when this is actually the condition of plastic hinge. So this plastic hinge will form when the whole section becomes plastic. So just when it becomes plastic, then this plastic hinge will develop. So that is the behavior of beam under bending or under flexure. Now based on this behavior, the beam section is classified into 4 categories, and it is actually classified based on these diagram that I will be showing you in the next part. I mean, in the next slide. Now look at this. Now, basically, the beam section is classified in four category. First one is called class 1 or plastic, which means when beam can have this kind of condition, which means it can apply, I mean, maximum stress, maximum yield stress can be in the whole section. So beam will experience maximum stress, plastification is occurring, and because of that, hinge is also forming. So this is the ideal failure that we want in our section. So if I section is experiencing the full plastification, or if it is able to achieve the maximum plastic moment because of the load, in that case, we will classify that section as class 1. Now, sometimes, as I said, as I discussed earlier also, that a beam may have other effect also, like the lateral torsion, lateral buckling. So because of that buckling, beam may not achieve the full strength, like I have shown you, like this is the I section, and corresponding to this is the stress diagram. So basically, sometimes what happens is because of this load, the beam may buckle and it may not achieve such kind of stress condition. In that case, we classify beam section in other three category also. So when we call it class 2, so you can see here, this is diagram, this is actually the moment rotation diagram. So because of the moment, beam is rotating, and because of that, curvature, beam curvature is forming. So at this, I mean, class 1 can have maximum curvature, and class 2 is experiencing full plastification, but hinge is not forming. In this case, plastic hinge is not forming. Before forming plastic hinge, it is failing or it is buckling. I will say here, plastic hinge is not forming, while in this case, plastic hinge is forming. Similarly, the third part, this one. So in class 3, you can see here, before, I mean, the outermost part is reaching the yield strength, but the lower, I mean, the lowermost part, I mean, this part is not reaching the plastification. And before that, it is failing or buckling. So this becomes class 3, which is called semi-compact. So class 1 is called plastic, class 2 is called compact, and class 3 is called semi-compact. Similarly, in case of class 4, we can say that class 4 is a kind of section which is not able to utilize its full strength. So plastic section can utilize its full strength, while cylinder section will fail at this stress. While it can take stress up to this one, it can have moment of resistance up to MP value, but at this moment of resistance, it is buckling or failing. And this is happening because of the higher width to thickness ratio. So width to thickness ratio, I'm referring to this one. This is the width of flange, say BF, and this is the thickness of web. So this BF by TW ratio, if it is higher, then it will go towards cylinder class 4, and if it is lower, then it will go towards the plastic. So basically, the beam section that we use in our construction hot rolled sections, they are basically fall under three category: class 1 or class 2 or class 3. But in case of plate girder, where uh, large plate sections are used, say for example, in case of plate girder, generally what we do is we join these plates using the welding. So in that case, this ratio, this is BF and this is TW. So this BF by TW is higher, and in that case, it may fall under this category also, cylinder. Okay. So basically, in our case, generally we will use hot rolled section, and hot rolled sections generally fall in, I mean, they can have plastic section, they may be class 2 compact section, they may be semi compact class section. Well, how do we define, how do we know whether our section is plastic, compact or semi compact? Well, in that case, what we will do is we will find out the width of flange, we will find out the thickness of flange, and we will find out the ratio, and based on that ratio we will classify whether a section is plastic, compact, semi compact. So that we will see in the when we will solve the numerical. Now we will discuss what is the modes of the failure. Well, ideally beam, I mean the failure for which we design our beam, the main modes of failure of beam can be bending failure, that is the ideal, or that is the common failure of the beam. Second is the shear failure. Well, shear failure can be in terms of web buckling or web crippling. Web buckling can be like this one. This vertical part is web, so this web can buckle like this. Or crippling. Sometimes web can buckle locally in this part. So this kind of failure is web crippling. So these two happens because of the shear failure. And deflection failure. Well, deflection failure is again related to the bending failure. Sometimes the beam may carry the required load, but at the cost of higher deflection. So IS code has specified deflection criteria also. As per table 6, we will follow the deflection criteria. Bending strength of beam. Well, bending strength of beam depends on various factors. We will consider all the failure mechanism of the beam, and based on that we find out the bending strength of beam. So generally the beam may fail under lateral torsional buckling if we don't support it laterally, or the flange local buckling may also occur. Similarly, web buckling may occur, and these type of failure may be either in the elastic range or in the inelastic range, or maybe we can say plastic range. So basically, the important aspect that we are supposed to consider while designing the beam are moments, shear, deflection, web crippling, web buckling, and lateral support. So all these criteria we will consider while designing our beam. So we will continue our discussion in the next part. Thank you.